Okay, this is the projectiles launched at angle problems. Okay, some things are very similar to the horizontal launched projectiles. Some things are different. What's the same between these two types of problems? Okay, AX is always going to be 0. That's going to be the same. And AY is always going to be negative 10 meters per second squared. That's always true. Now, VOY is not going to be equal to 0. VOY is always going to be VO sine the launch angle. And VOX is not going to be equal to VO anymore. VOX is going to equal VO cosine of the launch angle. Okay, so those are some differences and some likenesses. VOX will still remain constant because AX is 0. So at any point, as it's freely falling, VFX will equal VOX. That's the same as horizontal launch problems. Okay, if you look at this picture, you can see that VOY does not equal right here. VOY does not equal 0 at the beginning. It's positive, and it's VO times sine of theta. You got that on your equation sheet. As you proceed with free fall from launch, VY decreases. At the very top, you should see that VOY is 0. I'm sorry, VY is 0 at the very top, and VX is equal to VOX, like we said before. Okay, so at the top, it's not at rest. It's moving with an X component. It's not at rest, or else it would fall straight down. But VFY is 0 at the top of the trajectory. Then you can see that the VY flips to negative, whereas VX remains the same throughout the whole trip. Okay, let's move into actual problems now. So here, it says everything right there that I just mentioned. You might want to read that in your study guide. Okay, I'm going to skip these. You should be able to answer them. So, just to review, the ball is thrown with a velocity of 25 meters per second and an angle of 37. What is the vertical component of the velocity? Well, that's Vy. So Vy would be equal to V. That's That's the V times sine of the launch angle. So this would equal 25 times sine of 37. And you can do that in your calculator. That would be my answer. I'm still at electricity, so I'm going to let you solve that. And what would be the horizontal component? That's just 25. That's Vx. That equals V times cosine of theta. So that would be, in this case, 25 times cosine of 37. I'll let you solve that. Be sure you're on degrees. Okay, so these are just practice ones for parts of problems. Okay, this one, a ball is thrown with velocity they give you VO. They give you the launch angle. What is the horizontal at the exact top? Well, it's the same as the VOX because the x component stays the same throughout the whole trip. So this would be 20, would be V times cosine of 60. And you can solve that. Be sure you're on degrees. Okay, let's actually do a problem now. Okay, the very first step is to figure out the x and y components. And basically, you only need the y components on this one, but we could set up x and y table, but not necessary for something simple like this. So VOY is equal to VO30 times sine, because it's the y component, sine of 30 degrees. That's the launch angle. Boy. So I can do that without, I know the sine of 30 is 0.5. So VOY is equal to 30 times 0.5. That would be 15 meters per second upwards. So, what is VFY at the top? Well, it's 0. This piece shrinks to 0 at the very top. So, now you can use simple equation. D equals VLT. Okay, so we got VFVO. We have AY is negative 10, right? And so, we need to find time first, probably. But not really, because VF squared equals VO squared plus 2A change in Y. So 0 equals 15 squared plus 2 times negative 10 times change in Y. So 15 squared equals negative 20 change in Y. Actually, it equals positive 20 because I moved it to the other side. Okay, so change in Y equals 15 squared over 20 meters, whatever that is. Again, the power's out, and I'm going to use my calculator only when I need to with the candle. Okay, determine the maximum height reached by the projectile. So that's my answer once I calculate it out in meters. Okay, I didn't even need to find time because I could have solved that without time, not even paying attention to the x values because they didn't give me anything. The only thing I have with the x values is the VOX, and I don't need that in this simple problem. Okay, how about this one? So in this case, we want to find the range, maximum horizontal distance. So here's VO, here's the launch angle, and so we got to find x and y components. Well, at least the x one. So VOX equals V cosine of theta. So let's work it out. VOX equals 50 times cosine of what is it, 30. Okay, so I need to calculate this. Okay, so VFY, if you're thinking of the whole entire trip, here's VOY. VFY is going to be the same if it's over level ground, which I assume it is. VFY is going to equal the same thing as VOY, but negative. So VFY is going to equal negative 25 at the end of the trip. meters per second. Did you get that? Okay, the x stays the same, of course, the x component, but VFY shrinks as it gets to the top to 0, and then it builds up back to what it was at the same level. So VFY is negative 25. Okay, so we can use A equals VF minus VY. I'm sorry, VO over T. We're using the Y values. So VFY, okay, let's plug in numbers. We're trying to find T as the point. Negative 10 equals negative 25 minus positive 25 over T. So T is going to equal negative 50 over negative 10. Negative 50 over negative 10. Cross multiplied. And then I divide through by negative 10. So it takes total time of 5 seconds. You don't have to double it because I was determining the whole trip from start to finish. Okay, now that I got the time, I can find delta x, because change in x equals VOT plus AT squared over 2. And I'm going to use the x values. So VOX is 43.3. The time is here. The time is 5. AX is 0. So it cancels that whole thing out. I don't need that. So 43.3 times 5. 43.3 times 5. Okay, so I'm sorry. What I did was I calculate the time. I calculate the distance right there. Okay. Now, in the special case of the object landing at the same exact place that it was launched, landing at the same level that it was launched, you can use this equation right here. Range is equal to VO squared times 2, times sine of 2 theta squared, 2 theta over g. Now this equation is a range equation. It's limited because it only figures out the range if it hits the ground at the same level that it was launched. Okay, so let's just check to see that works. So VO is 50 squared times sine of 2 times, what's the launch angle? 30. So times 2 times 30 is 60. So the sine of 60. 2 times theta, 2 times 30 is 60 over 10. So let's see if that works on your calculator. And you get exactly the same answer. Okay, so this equation right there, this equation right here, is the last equation on your equation sheet. So it's only useful for finding the range if the projectile lands at the same horizontal level that it was launched. Okay, so I didn't have to do any of all this stuff for those kind of problems, but you can. Okay, so basically that's good. If it doesn't land at that level, okay, I did that one already. If it doesn't land at the same level that was launched, you can't do that equation. Okay, skipping those guys there. Oops. Okay, these are some concept questions right here. They're important. So these refer to projectiles launched at some angle, launch angle, not horizontal. So you can figure this out on your own by looking at that virtual lab that I assigned before, and just doing the angle launched ones instead of the horizontal launched ones. So which angles result in the same range? Okay, let's do that first question. Well, we can see what I gave you here, and you can see for yourself. For example, what if I shot one like, now you have to assume I'm keeping the VO the same in all these cases. So what if I shot something at 15 degrees? What gives you, for that given VO, gives you the same range, delta X? Well, you can see for yourself right here. Okay, so 75 degrees and 15 degrees gives me the same range right there, which looks like 5 meters for this given VO. Okay, let's do another one. How about the one that goes at 60 degrees? Okay, it looks like it hits, hits at about 8.7 meters down range. So what gives me the same one as that, the same delta X? 30 degrees. Now what can you see about these? 30 and 60. Then 15 and 75. What can you see? What relationship between the angles that give you the same range for a given VO? They're complementary. So complementary angles that add up to 90 degrees, they will give you the same delta X range for a given VO. Okay? So that's an important point. So you need to know that. Which angles result in the same range for a given VO? Complementary launch angles. So if I shot it at 40, which one which other launch angle would give me the same range for a given VO? 90 minus 40, so your answer would be 50. So you should be able to do that. What angle gives you the maximum range? Let's go to the next question. What angle gives you the maximum range? You already know that probably. 45 degrees. Because the X and Y components are the same on the VO. Which angle results in maximum height? Well, duh, 90 degrees. It goes straight up. If you shoot it at anything besides 90 degrees, it's going to have some X velocity that takes away from the Y velocity. How does air resistance affect the range? Obviously, drag will make the range get less than ideally without air resistance. How does air resistance affect height? Same thing. It's going to drag you in the Y direction or the X direction if you have air resistance. Okay, you can go to this link right here and see for yourself that I'm not making up this stuff. Okay, so there's that equation that I gave you, but it only can be true if you hit the same level that was launched. Okay, these are simple. You can do these from what I just said. Okay, these are the J problems, and you can't use that R equation to solve these, but you know what? Because of time restraints, I'm just gonna not do any J problems on my quizzes or my test for this section. Okay, so this is the end of this, the notes. So you should be ready for your formative quiz now on angle launched projectiles. I might put some of these J problems. No, let's just say I'm going to keep away from them because you have to use quadratic formula because you can't. It's just one of the things isn't going to cancel out in the equations as usual. Okay. Hope you guys get your electricity back, and us too. Our food is getting warmer and warmer in the refrigerator, and I'm gonna have to throw it out if Duke Energy doesn't get its game together soon. Okay, guys, see you at school. Bye. Oh, actually, on this one, you don't need the quadratic formula, so it's doable without the quadratic formula. So let's just set up the table, just for interest's sake, X, Y. So VOX is equal to VO cosine of 35. So that would be 25 times cosine of 35. That comes out to 20.48. VOY is equal to 25 times sine of 35. $14.34. That's what I get meters per second. Okay, AX is still 0. AY is -10. Let's see, what else do we know? We don't know the range. We do know the height. I mean, the displacement. Now, displacement is from the start to the finish. And if you look at the picture, the starting level is right here. Ending level is right here, down on the plane. So that's -20 meters. So they gave me -20 for y. I know that the OX, the fx at the end is going to stay the same as it was at the beginning. So it's 20.48. So we're supposed to find, if you look at the question, you're supposed to find the size and direction of the rock's velocity at impact. So I just want to find the speed, okay? I don't care about direction. I can use inverse tangent to find the direction. Okay, so so here's the rock, the meteor, whatever it is, big boulder. I'm trying to find VF right there at the end. Right there. Impact speed. Okay, so I had to find right here VFX and VFY. Well, I have VFX already. It's right there. It's 20.48. Okay, VFY I have to solve. Then I'll use Pythagorean theorem to find the VF. Okay, so let's find VFY. So I know A equals VF minus VO over T. Well, I gotta find the time first. I gotta find the time. How about this way? How about this way? How about this way? Okay. Maybe I can do it without finding the time. Okay, how about VF squared equals VO squared plus 2A change at Y. Since I know what the Y is, I can do this without finding the time. Okay, so these are all Y values that I'm trying to solve for. Okay, so I'm trying to find that guy so I can do Pythagorean theorem to find what VF is. So, VOY squared at the very beginning, VOY is 14.34 right there. Right there. Okay, so 14.34 14.34 squared plus 2 times -10 times -20. So let me write that better. Oh, anyway, let's just go. Okay, so let's work that out. Let's work this out on a calculator. I'll be right back. Okay, so I get 605.62 meters per second. That's what VFY is. Actually, that's what VFY squared is. That's too big for VFY. So VFY is equal to, but hold on, 24.61 meters per second. Okay, so now that I have VFY and VFX, to find VF right here, to find VF, I just take a squared plus b squared equals c squared, Pythagorean theorem. So let's see, VFX is 20.41, 20.48. So VF is VF squared plus VFY squared. And then you take the square root of that. That's Pythagorean theorem. So again, VFX is 20.48. VFY is 24.6. We just solved that one. So I get 32.02 meters per second for the final velocity. I could find the angle using inverse tangent, but the angle to the horizontal that it digs into the ground, but it's not necessary. Okay, if I wanted to find the range, right here, from here to there, I'd have to find the time using the y values, and then I could find the delta x. So let's just do that. You cannot use the range equation, that shortcut range equation that I gave you before. So let's try to find delta x right now. Maybe just go over to this page. Or up here. Up here would be better. So let's find the time first. So let's use this simple equation to find time. A equals VF minus VO over T. We're using the y values because we have all those things we need. So -10 equals VFY, which we found down here to be 24.6. Actually, it's -24.6 because it's on the way down. Okay, it's downwards, and then VOY is positive, and do we find that? Yes, VOY is 14.34 positive. And so the time is what we're looking for the whole trip. So T would equal 24.8. We Okay, you cannot use that R equation up there that I just wrote because the object doesn't land at the same level that it was launched at. So I'm not going to put this kind of problem on the test, but on the quiz, I might put parts of it. Okay, on your final quiz for this module. Okay, stay safe. I will see you at school next week. Hopefully.